Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. Title: The Lawgiver and the Labyrinth. In the vast architecture of mathematics, some names are load-bearing columns supporting entire edifices of thought. Others are decorative gargoyles, intricate and perhaps unsettling, perched on a single corner of the cathedral, their larger purpose forgotten by all but the most dedicated historians. The name of Józef Maria Hoene-Wroński occupies a peculiar space between these two states. To any student of differential equations, his name is familiar, attached to a clever and indispensable determinant that tests for the linear independence of solutions. It is a piece of solid, practical, and enduring mathematics. Yet this small, concrete immortality is a profound historical irony, for Wronski himself aimed at nothing less than the absolute. His life's work was the construction of a philosophical and mathematical system so vast, so ambitious, that it purported to unify all human knowledge, reform all sciences, and reveal the ultimate law of the universe. This grand project, his messianism, is now a curiosity. The enduring Wronskian is a tool. We are left with the ghost of a lawgiver whose universal decrees have faded into obscurity, while a single, almost incidental bylaw remains etched in every modern textbook. To understand this paradox, one must enter the labyrinth of Wronski's mind, a mind forged in the crucible of war, revolution, and the intoxicating intellectual ferment of 19th-century Paris. His journey began far from the salons and academies of France. Born in 1776 in the Polish-Lithuanian Commonwealth, Hoenen's early life was that of a patriot and a soldier. He entered the Warsaw Corps of Artillery, and his military career culminated in the Kościuszko Uprising of 1794, a valiant but doomed struggle for Polish independence against Russian and Prussian power. Captured by the forces of Alexander Suvorov, he was compelled to serve in the Russian army for several years before being released. This experience of national cataclysm, of a world order collapsing, and the desperate search for principles to build a new one, appears to have imprinted itself upon his psyche. When he finally arrived in Marseille, and then Paris around the turn of the century, he was a man seeking foundations, a universal order that might transcend the political chaos he had witnessed. He shed his military identity, immersed himself in the libraries of Paris, and remade himself as a scholar of breathtaking ambition. It was here that he adopted the name Wronski, and it was here that he began his assault on the fundamental problems of science. His first target was the very heart of mathematical analysis. The early 19th century was an era of profound consolidation and questioning in mathematics. The calculus, inherited from Newton and Leibniz, had proven to be a tool of miraculous power, yet its logical foundations were alarmingly shaky. Concepts like infinitesimals were used with an intuitive flair that troubled the new generation of mathematicians. Figures like Lagrange and Cauchy were striving to bring rigor to the field, to replace intuition with precise definitions and solid proof. Central to this project was the theory of functions and their representation as infinite series. The Taylor series, in particular, was a cornerstone of analysis, allowing mathematicians to express a vast range of functions as an infinite sum of powers of a variable. The formula f of x equals the summation from n equals 0 to infinity of the nth derivative of f, evaluated at a, divided by n factorial, all times the quantity x minus a to the power of n, was a thing of beauty and power, yet it was not a universal key. Certain functions resisted this expansion. Pathological cases, functions with discontinuities or points where they were not differentiable, fell outside its purview. The problem, as Wronski saw it, was the lack of a single supreme principle governing the generation of all series from a given function. He believed that the existing methods were mere special cases of a deeper, undiscovered reality. He thus set out to formulate what he called the Locid Supreme, the supreme law, a single formula that would stand above all others and provide the one true method for developing any function into a series. In 1810 he announced his discovery to the French Academy of Sciences, presenting a work of staggering complexity. The supreme law was not a simple refinement of Taylor's theorem. It was a complete reconceptualization. Wronski proposed that any function which he denoted phi of x could be expressed as an infinite sum of terms. This sum took the form, the summation from I equals 0 to infinity of a sum I times omega sum I of x. Here, the omega sum I of x terms were a chosen sequence of basis functions, and the coefficients, the a sum I, were the core of his discovery. These coefficients, which he derived through an intricate combinatorial process, were not simple constants. They were complex expressions determined by the function f itself and the chosen basis functions. These coefficients, later known as Wronski's Aleph functions, were defined using determinants built from successive differences of the functions involved. The sheer generality was breathtaking. By selecting different basis functions for the omega terms, one could, in theory, generate any type of series expansion one desired, be it a power series, a trigonometric series, or something else entirely. This was the work of a mind that saw mathematics as a system of absolute, hierarchical laws. The supreme law was intended to be the monarch of all functional relationships. Its innovation lay in its claim to complete universality, aiming to subordinate all known expansion techniques into a single overarching framework. The combinatorial machinery used to generate the Aleph function coefficients was profoundly original, a testament to Wronski's formidable powers of formal manipulation. He had constructed a labyrinth of symbols from which he believed the unified structure of all of analysis would emerge. The reception from the mathematical establishment, however, was not one of acclamation. The committee appointed by the Academy to review his work, which included the formidable Joseph Louis Lagrange, found the formulation hopelessly abstract and its claims unsubstantiated. The conditions under which this magnificent series would actually converge to the function it was supposed to represent were left vague. The law was presented as a kind of divine fiat, a formal truth, whose practical applicability and logical rigor were assumed rather than proven. For a mathematician like Lagrange, who had dedicated his career to algebraic clarity and analytical rigor, Wronski's work must have appeared as a piece of confounding, almost mystical, speculation. The supreme law was a monument, but it was a monument built on sand, lacking the solid foundations of convergence proofs that the new era of analysis demanded. It was a lawgiver's decree, but one that could not be enforced. This initial, titanic effort to solve the central problem of analysis defined the pattern of Wronski's career, a flash of profound, undeniable genius aimed at a problem of the highest order, yet ultimately undone by its own ambition and its creator's disregard for the pedestrian work of verification. The labyrinth he had built was magnificent, but few could find a clear path through it, including, it seemed, Wronski himself. The enduring determinant. The grand architecture of his supreme law, for all its ambition, now stands as a monument to a particular kind of intellectual overreach. Yet from the same workshop of Józef Hoene-Wroński's mind emerged a tool of such practical elegance and specific utility that it has become a permanent fixture in the mathematical toolkit. To find it, we must turn away from the search for a law governing all of reality and look instead to a specific pressing problem in the burgeoning field of differential equations. By the early 19th century, the study of linear differential equations had become a central preoccupation of analysis. Following the foundational work of Euler, Lagrange, and the Bernoullis, mathematicians understood that for an nth-order linear homogeneous equation, the general solution could be constructed as a linear combination of n fundamental solutions. The entire edifice of solving these equations rested on one critical pillar. These n solutions had to be linearly independent. This concept of linear independence is the formal mathematical articulation of what it means for a set of functions to be genuinely distinct, to contribute something unique to the general solution, rather than being mere multiples or combinations of one another. The problem was one of verification. Given a set of candidate solutions, how could one rigorously and efficiently prove their independence? The methods available were often ad hoc, involving cumbersome algebraic manipulations or arguments that lacked a universal computable procedure. The field required a clear, decisive criterion. It was in this context that Wronski, in an 1812 paper submitted to the French Academy, introduced a concept of startling clarity. He devised a specific determinant, an object constructed directly from the functions in question. For a given set of n functions, say f sub 1 of x, f sub 2 of x, and so on up to f sub n of x. The determinant is formed in a beautifully systematic way. The first row consists of the functions themselves. The second row is populated by their first derivatives. The third row contains their second derivatives. This pattern continues, row by row, until the final nth row is filled with the n-first derivatives of each function. This square array of functions, and their successive derivatives, when its determinant is calculated, yields a new function of x. Wronski's profound contribution was the theorem connecting this new function to the question of independence. He demonstrated that if this determinant, which we now universally call the Wronskian, is non-zero for at least one point in the domain where the functions are defined, then the original set of functions is linearly independent. The abstract, sometimes elusive property of linear independence was thereby transformed into a concrete, computational test. One simply had to construct the matrix, calculate its determinant, and check if the result was identically zero. It was a bridge from abstract structure to tangible calculation. Let us consider a foundational example, one taught to every student of the subject. The simple harmonic oscillator, a system describing everything from a swinging pendulum to an oscillating spring, is modeled by the equation, the second derivative of y with respect to x plus y equals 0. Two well-known solutions to this equation are sine of x and cosine of x. To form the general solution, we must confirm they are linearly independent. Using Wronski's method, we construct a 2-by-2 determinant. The first row contains the functions themselves, sine of x and cosine of x. The second row contains their first derivatives. The derivative of sine of x is cosine of x, and the derivative of cosine of x is negative sine of x. The calculation of this determinant is straightforward. We multiply the main diagonal and subtract the product of the off-diagonal. This gives us sine of x times negative sine of x minus cosine of x times cosine of x. The expression simplifies to negative sine squared of x. Factoring out -1, we are left with -1 times the quantity sine squared of x. The expression in the parentheses is, by the fundamental Pythagorean identity, equal to 1. The Wronskian is therefore the constant function -1. Because this value is demonstrably non-zero, Wronski's criterion is satisfied. The function sine of x and cosine of x are rigorously proven to be linearly independent, providing the solid foundation upon which the general solution, c sub 1 times sine of x plus c sub 2 times cosine of x, is built. The elegance of this tool secured its place in the mathematical canon. It is a workhorse of the field. Its utility extends into more advanced techniques, most notably in the method of variation of parameters, a powerful procedure for finding solutions to non-homogeneous linear differential equations. In the very formula for the particular solution derived by this method, the Wronskian appears explicitly in the denominator, playing a crucial role in the mechanics of the calculation. Its presence is not incidental, it is fundamental to the structure of the solution space. This contribution represents Wronski's most direct and undisputed legacy. For generations of physicists, engineers and mathematicians, the name Wronski is not first associated with a supreme law of creation or a messianic philosophy. It is attached to this determinant. It is a concept encountered not in obscure historical treatises, but in the second or third year of every undergraduate science and engineering curriculum across the globe. It is a living piece of mathematics, a tool sharpened in the 19th century that remains indispensable in the 21st. The determinant's survival is a quiet lesson in intellectual history. While vast, all-encompassing systems of thought can crumble under the weight of their own ambition, a single perfectly formed and profoundly useful idea can achieve a kind of immortality. The Wronskian operates today on blackboards and in the heart of computational algorithms, entirely unconcerned with the cosmic destiny its creator had envisioned for himself and for all humanity. The Wronskian, a testament to rigorous mathematical insight, stands in stark contrast to the philosophical edifice Wronski erected alongside it, a monument to ambitious, yet ultimately unrealized, metaphysical aspirations. This seemingly disparate duality, however, offers a profound glimpse into the intellectual landscape of the early 19th century and the mind of its architect. For Wronski, mathematics was not an isolated pursuit, but a crucial element within a far grander system, a system he termed his absolute philosophy, a project that sought to unify all knowledge under a single overarching principle. The intellectual climate of post-Napoleonic Europe provided fertile ground for such ambitious undertakings. The Enlightenment's emphasis on reason, while undeniably transformative, had also fragmented knowledge into specialized disciplines, leaving a perceived void at the heart of human understanding. Wronski, acutely sensitive to this perceived intellectual and spiritual crisis, believed humanity had lost its way, adrift in a sea of disconnected facts and competing theories. He envisioned a new synthesis, a framework capable of harmonizing disparate fields of inquiry and revealing the fundamental principles governing the universe and human existence. This synthesis manifested itself in his absolute philosophy, a system characterized by a potent blend of rationalism and messianism. Far from a mystical or purely religious doctrine, Wronski's vision was grounded in a highly rationalistic approach, attempting to derive the ultimate purpose of creation and history through a rigorously defined supreme law. This loi supreme, as he called it, was not merely a mathematical formula, but a fundamental principle governing all aspects of reality, from the smallest particles to the grand sweep of cosmic evolution. It was a framework designed to unlock the secrets of the universe and reveal humanity's place within it. His philosophical system, a distinct form of Polish messianism, differed markedly from the more poetic and less rationally structured versions espoused by some of his contemporaries. Wronski's was a system predicated on absolute reason, a deductive architecture intended to lead humanity to a state of ultimate understanding and perfect social harmony. The ambition of his project was breathtaking in its scope. Wronski aimed not merely to advance specific scientific fields, but to reform human knowledge itself, to create a universally applicable system that would resolve all intellectual and social conflicts. This ambition stemmed from a profound belief in the power of reason to unveil ultimate truth, a belief that permeated both his mathematical work and his sprawling philosophical system. His rigorous mathematical explorations, therefore, were not merely intellectual exercises, but essential components of a larger, divinely ordained project. The historical significance of Wronski's absolute philosophy lies not in its lasting influence on mainstream thought. It largely failed to gain widespread acceptance, but in its profound reflection of the intellectual currents of its time. The 19th century witnessed a surge in attempts to construct all-encompassing systems that could unify science, religion, and philosophy. Wronski's system, with its blend of rigorous rationalism and messianic fervor, exemplifies this ambition, revealing the profound desire to find a single unifying principle underlying all aspects of existence. His work serves as a valuable lens through which to understand the intellectual anxieties and aspirations of this pivotal era. It underscores the powerful appeal of totalizing systems, however ultimately flawed, in a world grappling with rapid change and the perceived fragmentation of knowledge. The contrast between Wronski's mathematical legacy and his philosophical ambitions is not a simple dichotomy, but a complex interplay of intellectual strengths and limitations. His capacity for rigorous logical deduction, evident in the creation of the Wronskian, coexists with a tendency towards grand all-encompassing systems that ultimately proved unsustainable. This tension, however, is not a weakness but a reflection of the intellectual landscape he inhabited, a landscape where the Enlightenment's emphasis on reason collided with the romantic yearning for holistic understanding and a sense of cosmic purpose. His story is a testament to the human capacity for both precise, enduring intellectual contributions and for the potentially overwhelming allure of speculative, all-encompassing systems. To understand Wronski is to understand the inherent tension between the focused pursuit of specific truths and the irresistible human impulse to seek a unifying framework for all of existence. The legacy of Wronski, therefore, resides not only in the enduring mathematical tool he bequeathed to posterity, but also in the profound questions his ambitious, ultimately unsuccessful philosophical system continues to raise about the nature of knowledge, the limits of human reason, and the enduring quest for ultimate truth. The next portion of this essay will explore the less triumphant, yet equally revealing aspects of his life, illuminating the human complexities that lie behind the creation of both a powerful mathematical concept and a sweeping, albeit ultimately unsuccessful, philosophical system. The final years of Józef Maria Hoene-Wroński's life present a poignant counterpoint to the brilliance of his mathematical achievements. His unwavering belief in his own philosophical system, a grand synthesis he termed the supreme law, led him into increasingly bitter conflicts with the established scientific community. The French Académie des Sciences, a bastion of Enlightenment rationality, proved a particularly resistant adversary. His pronouncements, often delivered with a messianic fervor that bordered on the theatrical, frequently clashed with the cautious empiricism favored by the Academy's members. These clashes were not merely intellectual disagreements, they were deeply personal battles, fueled by Wronski's growing sense of isolation and the persistent financial insecurity that dogged him throughout his life. His accusations of plagiarism, leveled against prominent figures such as Lagrange, further exacerbated his strained relationships with the scientific elite. These accusations, while perhaps born from a genuine belief in the originality of his own work, were ultimately unproductive, contributing to his marginalization within the scientific community. The intensity of his conviction, while admirable in its unwavering commitment to his ideas, ultimately hindered his ability to engage in constructive dialogue and find common ground with his peers. His pronouncements were not merely statements of intellectual difference, they carried the weight of a man feeling profoundly misunderstood, his genius unappreciated in a world that seemed unwilling or unable to grasp the scope of his vision. The irony is palpable. The creator of the Wronskian, a tool of undeniable practical utility in diverse fields of mathematics and physics, simultaneously championed a philosophical system that proved ultimately unfruitful. His attempts to secure financial stability by applying his inventive mind to practical technologies underscored the tragic disparity between his theoretical brilliance and his material circumstances. Projects like the prognometer, a device intended to predict the future, and the chenille articulae, a pioneering caterpillar track vehicle, reveal a mind capable of both abstract mathematical reasoning and ingenious mechanical design. Yet, these inventions, born from a fertile imagination, failed to translate into the sustained financial success that would have allowed him to fully dedicate himself to his intellectual pursuits. His struggles were not merely a matter of unfortunate timing or lack of resources. They reflected a deeper incongruity between the boundless ambition of his philosophical vision and the pragmatic realities of his existence. The image of Wronski toiling in relative obscurity, his revolutionary ideas largely ignored, while simultaneously crafting elegant mathematical solutions that would endure for centuries, is a striking one. It highlights the complex and often paradoxical nature of genius. His relentless pursuit of a unified system of knowledge, a quest for absolute truth that consumed him, ultimately overshadowed the enduring value of his more focused, precise contributions. His story is not a simple narrative of success or failure. Instead, it is a multifaceted portrayal of a man wrestling with both the exhilarating potential and the inherent limitations of human intellect. The enduring legacy of Hoene-Wroński thus presents us with a compelling paradox. How do we reconcile the creator of the concise, elegant, and enduringly practical Wronskian with the fervent proponent of a vast, ultimately unsuccessful philosophical system? His life is not merely an academic footnote, it is a microcosm of the larger tension between rigorous scientific investigation and the pervasive human desire for grand unifying narratives. The Wronskian, a testament to his analytical precision, stands in stark yet illuminating contrast to his more speculative philosophical ambitions. His story, therefore, becomes a powerful lens through which we can examine the very nature of genius, the potential pitfalls of intellectual overreach, and the complex interplay between focused inquiry and the all-encompassing pursuit of ultimate truth. Hoene-Wroński's life embodies a crucial transition. He was a product of the 18th century Enlightenment, inheriting its emphasis on reason and precise mathematical analysis. Yet he also embodied the boundless, often reckless, speculative ambition characteristic of the burgeoning romanticism of the 19th century. His pursuit of a single overarching system is a testament to the romantic impulse, while his creation of the Wronskian showcases the enduring power of Enlightenment rationality. He stands as a potent symbol of this pivotal moment in intellectual history, a figure who bridged two distinct epochs, yet ultimately found himself stranded between them. His legacy, therefore, is not simply the sum of his achievements and failures. It is a compelling narrative that invites reflection on the nature of intellectual ambition, the limits of human understanding, and the enduring human quest for meaning in a complex and often unpredictable world.
The enduring power of his story lies precisely in this profound and enduring contradiction.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.